Hello, ladies and gentlemen. I apologize for my absence today. My child came down with fever at the very last minute and at the very end of the school day, so he can't go to school for 24 hours. Here's hoping he'll be all good so that we can go ahead and move on. What I've decided to do is go on to a topic called linear approximation. It's a little bit simpler than the last ones, and whereas the last two topics that we talked about, the derivatives of inverse and the derivative of inverse trig functions, which we'll take a look at when we get back, when I get back, well, those are a little bit strange and big and long and gross and in general just not particularly fun. The next few topics are going to be incredibly important. The first one is actually something that we've done before. This concept of linear approximation. And the way it works is kind of like this. Let's say I wanted to find the cubic root of 127. And if I were to ask you what the cubic root of 127 is, if I asked you, the cubic root of 127 to 5 decimal points, you wouldn't be able to do that, theoretically. Naturally, you have a calculator. But we wouldn't be able to just come up with a number for that off the top of our head. Now, we would probably be able to estimate it somewhat. We know that it should be slightly larger than 5 because we know that 5 cubed is 125. But beyond that, and knowing it'll be larger than 5, we're not sure what that number would be. Now, I realize what you're thinking is, well, we've got calculators, so why would we be worrying about that? But just as a quick aside on history, remember that the calculators that you're using, these TI Inspires, they're fairly new. They came out 2011. Graphing calculators, as we personally know them, really weren't popular, really weren't feasible as something that we would be able to get into schools until even the mid-90s for price point. And then even then, calculators weren't really utilized by people until, really weren't popularized and used until the 80s, with a few people in the 70s having them. But calculators were, for the most part, something that weren't for laymen. You looked up things like cubic roots in tables. You looked up, or you learned how to use a slide rule. So this is really a method of coming up with at least a decent approximation that's fairly, that has really only fallen on the wayside recently. So what linear approximation basically does is it says that if I take a curve and create a tangent line, so you can see that we have a y equals f of x, and that's my function, and then we have a y is equal to the L of x, some tangent line function here. And if we were to look at this curve and this tangent line, and if I wanted to know this ordered pair right here, this a comma f of a, we wouldn't be able to come up with that necessarily, but if I could make a tangent line, well, while that may be a really gross number to calculate, this point right here, where if I look at this as a L of a, that's a fairly close approximation. And in fact, the closer we get, I called it A, I probably should have called it B. I apologize. Let's real quick change those to B's. There we go. Look at that creativity. Didn't realize I had A down here. But if I have that, this is a fairly close approximate. In fact, the closer we get, the better the approximation will be until we're exactly on this tangent line point. This is the concept of linear approximation, that we're creating a tangent line, thus the linear, and we're going to evaluate a point on that line that's close to, but not quite equal to, the functional value. Now, one of the things that we do want to know is whether we have an over and under approximation. So what I would like you to do is I would like you to pick a point anywhere on this curve. So I'll pick here, I'll pick here, I'm going to pick here, and I'm going to pick here. Pick any 4 points along those curves and draw a tangent line. I'll give you a moment to do that. I myself, I'm going to go ahead and now I've got this cool line function, so I might as well use it. That looks kind of tangent-ish. All right, we'll draw a tangent line, it looks like through there. It looks like maybe a tangent line would go through somewhere like that. All right, so hopefully you have 4 graphs with tangent lines. And what I would like you to do is I'd like you to look at these tangent lines. And you will notice, if I were to look at this particular function, you would note that between these 2 endpoints, this is always concave up, these 2 curves. And if that curve is concave up, you'll notice that in both cases, and hopefully in the 2 that I drew, and hopefully you pick 2 different points, that no matter where I put a point along this curve, the line will always be below the curve. That's kind of that concave up concept, is that the curve is curving up from the line. You'll notice that the line is always below, which means that if I pick a point anywhere on this line, these points on the line are always below the point that coordinates with those these line points. These points on the curve are going to be above it at all times. Therefore, the line will always be an underestimate. Likewise, in a concave down function, a curve that some curve that goes down from a line, we can see that those are going to be over approximations. The points on the line are always over the points on the curve. Nothing crazy. But we are going to have to practice the justification. You'll see in the justification, I'm always going to state that the approximation is always an over and underestimate. I'm going to show how I know that a function is concave up or concave down. So I'll show that the second derivative is negative or positive. That's the most likely one, although you may see on occasion f prime is decreasing or increasing. And you'll notice that my interval will always be based on the point that I'm talking about here and the point that I'm using for my tangent line. Again, I know that that's a lot, but and we'll get a chance to work that a little bit more. In fact, let's go ahead and take a look at that now. So we have f of x is equal to x squared times 4x plus 1. And we want to write an equation for a tangent line to the graph of f at the point where x equals 3. So to do that, I need to find f of 3. And I need to find f prime of 3. So I look here and f of x is x squared times, so that one I probably will just go ahead and I'll go, this is what, 3 squared times 4 times 3 plus 1. So what is that? That's 9 times 13. So 90 plus 27 is 117. However, if I'm going to do f prime, I probably don't want to do this because this would be a product rule. I'm much bigger fan of 4x to the third plus x squared. So f prime of x becomes 12x squared plus 2x. Now I may choose to factor out a 2x here, call that 2x, 6x plus 1. Because that'll be easier to evaluate this. Oops, 6 times 3 plus 1. Fantastic. So what is this? This is 6 times 19. So 6 times 20 would be 120, less 6 is 114. And we say, well, then this is going to be y minus 117 equals 114 x minus 3. Now, this is really this is going to be an unusual step. This is all, again, this is just doing a linear tangent line here at the point here. I'm actually going to do one thing that I haven't done ever, and that's move this 117 over. And it will make more sense as we move on through the rest of the problem to the next step, where I ask you to use the equation found in part A to approximate f of 2.97. So f of 2.97, what does that tell us to do? It tells us to plug in the 2.97 into this function. Now, I don't know about you. I have no interest in squaring 2.97 and distributing it, nor do I have the interest in cubing 2.97 and then squaring 2.97 and then multiplying that before and then combining all those like terms. It's going to be gross. So instead of having to do a lot of extra work, what I can choose to do is approximate that as the y value evaluated at that 2.97. See, what I can do is instead of finding the curve in the exact point, I can say, well, this is just 114 times 2.97 minus 3 plus 117, or written slightly different, 114 times negative 0.03 plus 117. Now, I'm not saying that this is significantly better, and far from it. This is kind of gross and disgusting, and it's not necessarily what I would want to have to multiply, but it is a whole lot easier than what we had before. So if we did this and we wanted to calculate what this was, we could go ahead and just calculate this out. The 114 times negative 0.03 turns out to be negative 3.42. And if we combine those, we get 113.58. Now, if you wanted to use a calculator, you could of course check to see how close we were on that particular problem. But that's linear approximation. It's a whole lot easier to calculate those numbers than the ones before. Now the last part asks is the approximation greater or less than the actual value. So to do that, we want to identify the concavity of the function between 3 and 2.97. So what I'll do is I'll take the second derivative of x. And if I do that, again, I'm not going to use this portion. I'm going to use the 12x squared plus 2x. Let's call that 24x plus 2. And we'll set that equal to 0, and I'll figure out that x is going to be negative 1 over 12. So I go ahead, I take a look at this particular setup here, f double prime of x, and I'm going to come up with the chart. This becomes a negative to a positive, which is helpful. And what that means is that anything larger than negative 1 over 12 is going to be a concave up function. So we can say since f double prime of x is greater than 0 or is positive on, and the two numbers I'm going to use, 2.97 to 3. So it's always going to be the approximating number and then the tangent point. So since this is concave up on here, we can see that we have a concave up function, which means my line is underneath. We can say the approximation is less than actual. The part that's usually skipped the most here, we come up with the concavity and everybody's pretty good with that. It's that little piece right there where you got to talk about the space. The reason why that turns out to be important, actually, is that if I have a concave down function all the time, of course we've already seen that a line will be over that, but if we have something that changes concavity in the middle, then what winds up happening is sometimes we can actually wind up getting a situation where, yeah, if I draw a tangent line here, everything's good, but then when it changes concavity, I go from an overestimate to an underestimate, and that's where we get sometimes a little fishy. By the way, if there is a change in concavity there, there is a major problem. Oh my goodness, I can't find what I'm looking for. If there is a change in concavity, we have a little bit of an issue, and then they're never going to ask us this part here, part C, because then we'd have to find the actual, and if we have to find the actual, then what on earth was the point of doing that anyways? Alright, suppose that the only information we have about a function is that f of 4 is negative 2. Cool. And the graph of the derivative is shown here. Now notice that they don't give us anything else. I hate that this is not labeled, so I'm going to say that this is f prime of x so that I know that. Use a linear approximation to estimate f of 3.9. So linear approximation, I see the word linear, I have to make a line. The only line we ever make in calculus is a tangent line. So I need to find a point, which is really easy. They gave it to me. Those of you are like, where? It's right there. Bam. The other thing we need to find is a slope. So we need to find f prime at 4. Since this graph is f prime, we go, cool, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And we create from those two pieces of information, y plus 2 is 6 times x minus 4. And because I want to use it as an approximation, I rewrite the equation as just a y equals. Now, this would give you 1 point writing the equation of the tangent line. And then the final step is to come up with an approximation for f of 3.9. Now this time I don't have an equation. I don't have anything to use, so I couldn't even hand calculate this if I wanted to. All I can do here is try to evaluate y when x is 3.9. So we look at 6 times 3.9 minus 4 minus 2, which turns out to be 6 times negative 0.1 minus 2, negative 2.6. That would give us the second point. Last but not least, we want to know, oh, what color am I going to use? We're going to use red again. No, we're not going to use red. We'll use black this time. Is the estimate too high or too low? Well, when I look at this section, I use the 4, which is right there. This is 3.9. You'll notice that f prime is decreasing. So we say f prime of x is decreasing on, and the 2 points we've got are 3.9 and 4. Therefore, f is concave down. The estimate is, and if I got a concave down function, my tangent line is above the curve, so the estimate is too high. Again, just like a bunch of other questions, if I'm dealing with concavity, I'm drawing a picture just to make sure I don't make a mistake. You know, there are so many ways that I can mess things up that I just don't want to have to deal with it. Please don't tell me that f prime is concave down, therefore f is concave down. That's a terrible reason to think that something's going on. Remember that it's the relationship for f being concave down, if we're using our fun box, is if I want concave up and concave down, I want either f increasing or f prime increasing or decreasing, or f double prime being positive or negative. The last question that we're going to do together is the 2014 question number 6. We're going to consider the differential equation dy dx is equal to 3 minus y times the cosine of x. That looks gross. And what the heck's the differential equation? Don't worry about that yet. That is coming soon. That'll be a second semester discussion. On top of that, we're going to let, but for those of you who are really curious and it's bothering you, all differential equation means is that it's a function with a dy dx or any other version in it. And what I mean by any other version is the second derivative, the third derivative. As long as it's got some weird dy dx thing going on in it, it's a differential equation. So that's what we're looking at. Now let's let y equals f of x be a particular solution to the differential equation. Okay, that means that if we got rid of the derivative, y equals f of x would be the thing that we took the derivative of to get to this. So again, not necessarily something we need to know right now. With the initial condition, f of 0 equals 1. That should set our Algebra 1 senses tingling at this point in time. That's right, Spider-Man. Our Algebra 1 senses are tingling. F of 0 is equal to 1. I know what that means. That means that I have a point. I have the point 0, 1. Fantastic. The function f is defined for all real numbers. That's cool. What does that mean? It means that f is continuous. No, actually it isn't f is continuous. I apologize because there could be a jump. But it does mean that there are no weird holes or gaps, although there is a derivative, so that's helpful too. B, write an equation for the line tangent to f of x at the point 0, 1. So, here it is. Clear as day. Write the equation of a tangent line. So I need a point, I need a slope. Where do we get the slope from? Well, slopes come from differential equations, dy dx. So I'm going to take dy dx, I'm going to evaluate that at the point 0, 1. So wherever I see a y, I'll substitute in a 1. 3 minus 1. Wherever I see an x, I'll substitute in a 0. The cosine of 0 is 0. 3 minus 1 is 1, sorry. 3 minus 1 is 2. So this becomes just 2. So I can make the equation of the tangent line be y minus 1 is equal to 2 times x minus 0. Cleaning this up a little bit, we'll say y is equal to 2x plus 1, which is kind of weird. Told me not to write it ever in point slope intercept form, and you did. No, I wrote it in point slope form, and it just simplified easily that way. The last step it asks us to do is to use the equation to approximate f of 0.2. Again, remember, I don't actually know anything about f of x other than it's a solution. So what I'm going to do is f of 0.2 is approximately y evaluated at 0.2. So we take a look at this, and we would get 2 times 0.2 plus 1, or 1.4. Notice that there is no question about, I don't want you to have to take a derivative of two variables, so I'm never going to ask you with two variables whether this is an increasing or a decreasing function. That gets, or a concave up or concave down function. That gets a little too weird. But this is the basic steps, folks. Make a tangent line, plug in a point, and if it asks you about concavity, see what you can do. There's probably about 20 minutes left in class at this point in time. So what I would like you to do is I would like you to get a little bit of an attempt at some of these. Not necessarily answer them completely. Specifically, I would like you to really take a look at this 1991 AB3 question. Should be something that is definitely doable. We can write the equation of a tangent line. We can write, we can come up with an approximation. That shouldn't be too bad. What I would also like you to do is I would like you to consider A and B here. And we will take a look at C in a little bit. If you want to get a shot at it, go ahead. And finally, do we want to do this one? Yes, let's give this one a go. So if you manage to get through all four of these, I would be really surprised. There's a lot of stuff going on these. But give those a shot. And my goal is tomorrow, with me being back, knock on wood, that we'll get a chance to discuss these questions, play with them, try them out, see what the solutions are, and that you can ask questions regarding this. I cannot stress this enough, folks. This is super important. This linear approximation thing is going to be something that, you know, in this concept of, you know, just in math history, this is still fairly fresh. In the concept of just trying to come up with a quick approximation, it lets us get at least a decent solution out of a problem. In the world of being somebody who, you know, really just wants to pass the test, this is something that is going to probably be worth about 5 to 8 points on the AP test. So it's a big deal knowing how to utilize all these pieces of information. And you're going to notice that really there's nothing new here. This is just taking the linear tangent lines that we talked about way back at the beginning of derivatives, and now we're putting an application to it. So it kind of brings us full circle on our derivative topics, starting talking about tangent lines and finding slopes of tangent lines, to now taking that tangent line and applying it inside a situation. I hope that you have a good rest of your day. I appreciate your time, and I look forward to hearing your questions tomorrow.